Selamat pagi semuanya! Recently I have been doing a video series about 3D graphics starting with triangle rasterization and texture mapping. In that series I created some example code. Today it is time to continue that project. This episode will focus mostly on refactoring. Refactoring is a topic that is not often discussed publicly. There are many good guidelines for maintainable programming, but what happens when the requirements change, or when you discover after the fact that your code is not as maintainable as you hoped? If you keep coding and ignore the need for refactoring, you will accumulate what is called technical debt. It means that the longer you go without refactoring, the more expensive it will become to add features in terms of development time. Technical debt is like grains of sand that keep accumulating in the gears that keep your machine running. For instance, a technical decision that you made early on may end up slowing down your work later as more features are added, and until the issue is recognized and addressed, it will cumulatively make your work more and more costly in terms of time and your own mental health. Every now and then you will need to acknowledge the fact that your program may need maintenance that does not actually fix any problem or add any new features. It is my professional experience that this kind of work is by far the hardest thing to sell in a corporate environment. It does not immediately result in tangible improvements. It may not make your program faster or more reliable. You may catch and fix some bugs while refactoring, but primarily it is an investment in future development work. It is easy to blame the developer in this case. Why didn't you make it perfect in the first place? Well, duh. Nobody's perfect, that's just how things are. In this 3D rendering video project of mine, I have deliberately introduced refactoring every now and then to remind you of its importance. This project is actually a very good representation of a typical corporate programming project. There are tangible objectives you have to achieve, but precious little time budgeted for the job. For me, the tight budget of time comes from the need to keep videos concise. Shorter videos gain better views than longer videos. Videos that do impressive things often gain better views than videos that have a lot of lull time. So I keep accumulating technical debt, which I need to address in order to keep this series running smoothly. The first thing that I addressed was my vector mathematics library. Some people have criticized it for being too complex and difficult to understand. While I have my reasons, I also acknowledge this fact. And to address the problem, I added two helper functions, asTuple and asArray, which flatten any parameters given to them into a single tuple or a single array. Then I rewrote the mul function, which I renamed into reduce to better indicate its intended purpose. By using these two functions I added, resulting in code that is much more visually pleasing and easier to understand. For the user of my library, this does not cause any need to change their code, but they now have two extra helper functions which they can utilize, and if they want to read the library, it is much easier to do that than before. Then I focused on the main module, which had grown long and complex by the 12th example showcased in the series so far. As many of you probably know, what you see on the screen in these presentation-oriented videos is not me typing the code. It is neither any person typing nor is it sped up footage, except for some pauses where I adjust the timings in post-process to match my narration. The computer is typing by itself. I wrote a set of tools that let me design in advance, down to smallest detail, how exactly to present the code on the screen. The process is refined somewhat from when I last made a video explaining how it works. For instance, it now uses that terminal and Joe instead of that editor and DOSBox. And the input generator is now written in C++ rather than in PHP, but the process still has certain limitations, such as that it can only work on one file at a time. It is one of the reasons that you may get the impression from my videos that I like to have everything in one file. It is not a good principle, so I added support for a feature that lets me evict parts of the source in separate files. Here I evicted the polygon tessellation, polygon clipping and the slope interpolator, all of which are generic by their nature, into template header files, much like I had already done with the vector functions and with the polygon rasterizer. Next I got an idea. I know I made a big deal in the last episode about the compile time for loop in C++17, which I erroneously labeled as C++11. I realized that you can actually do just fine with std_apply, even if you need special actions for particular indexes or to skip particular indexes altogether. Just define those indexes as parameters and omit the names for those parameters that you don't care about. It is kinda hard to explain, and I totally fail at trying, but the outcome is that the code becomes much simpler and cleaner looking, and there are no longer any hard-coded numbers anywhere in the source code. We don't even need to know how many elements there are in those objects that the code is dealing with. I love it when the code becomes so generic that you can totally disregard details that are only relevant for the caller. But then I got another idea. You know, in my video projects there are often telltale signs that the design has evolved during the video production process. For instance, in the first episode of this series, I went painstakingly through this list of different triangle shapes. The idea was that your rasterizer needs to deal with all possible combinations where the next point may be, on the left side, on the right side, or in the same column as the previous point. While it can serve as a nice checklist to make sure your implementation is correct, ultimately it was totally redundant for the purposes of the video. A few of you pointed this out to me. I also pointed out that simple things are best and that a triangle is the simplest possible polygon. I walked you through an algorithm that identifies whether the bend is on the left side or on the right side of the triangle, and then calculates the x-coordinates simultaneously on both sides by interpolating between the start and end coordinates, and draws horizontal lines between those 2 points on each scan line. Well, after thinking about this for a while, I realized that this algorithm is actually rather trivial to extend to work with arbitrary polygons, such as this octagon. It has 8 points and 8 edges, and these 8 edges form a connected ring. Some of these edges are on the left side of the polygon and some of them are on the right side. The top and bottom sides are horizontal in this example. The process is almost exactly the same as the last time. This time we cannot sort the points in ascending order of the y-coordinate because we have to maintain the ring property. If we sorted the points, we would get a polygon that looks something like this, and that's definitely not what we want. Instead, we search the list of points and find the single top leftmost point and the single bottom rightmost point. These are the starting and ending positions for the rasterizing process. Next, we have to determine which way the points are arranged. Are they clockwise or are they counterclockwise? One of these directions is for the left side and the other is for the right side. You cannot solve this by simply comparing the x-coordinates. For example, here point 1 is on the right side of point 2, the exact opposite of the correct conclusion for which side of the polygon they are. The correct way of determining the winding direction is to use the vector cross product, and the formula is shown on the screen. The sign of the result indicates which winding direction the points were supplied. You can do this with any 3 successive points in the polygon, and in fact, if some of the points are coplanar, you will have to try it with several triplets until you get a clear enough indication of the winding. Or you could just hardcode the assumption that all polygons have a particular winding. Now that we have discovered whether to go forwards or backwards in the chain, to go clockwise or counterclockwise, the rasterization begins. We create 2 slopes, one for the left side and one for the right side, both starting from the top left point. Then we compare the y-coordinates to see which one is earlier and set an event marker there, and also remember which point was at that y-coordinate. Here the event is immediately encountered. The point on the right was at that y-coordinate, so we advance the edge on the right side and calculate a new slope. Then we compare their y-coordinates to see which one is earlier. Here the next event will be on the left side, 3 scan lines down. We can therefore render 3 scan lines. When we reach the y-coordinate where the next event is, we once again pick a new slope for that side. This time it's on the left. Then we compare their y-coordinates to see which one is earlier. Now the next event is on the right side, again 3 lines down. When we reach the next y-coordinate, we pick a new slope for the right side and compare y-coordinates again. The next event is just 2 lines down, and we select a new slope for the left side. 4 lines later, the next slope is on the left side and the next event will be at the bottom row. When we reach this event, this time the left side and the right side are both simultaneously at the same y-coordinate. It doesn't matter which one we process, we could pick either one. Here, by chance, my code picks the slope on the right side and discovers that this slope has reached the end vertex, so the rendering is terminated. The polygon rendering is finished successfully. So this is the algorithm that I now have to put into code. First, I made some tiny refactoring improvements to the existing code, such as adding include guards in the header file and utilizing the isTuple concept from my math header. And then I created a new function, rasterize polygon, by copying the rasterize triangle function. I replaced the 3-point parameters with a single range of any number of points, and adjusted the concept requirements accordingly. Then I replaced the code that sorts the 3 points in topological order with code that searches the list of points and finds the top left and bottom right vertices. This is done by using the std_min_max element function and giving it a custom comparator that compares the y-coordinate and the x-coordinate. Next we will need to deal with the winding direction as I specified earlier. It begins by taking the x and y coordinates for the first 3 points and using the cross product formula as I explained earlier. If we get a good enough result, we accept that result. If we don't get result that we can accept with confidence, we simply don't render anything. In that case, the polygon is probably too narrow for there to be any pixels in it. However, this calculation is the most complex part of the polygon rasterizer, and for many applications it is totally unnecessary. Because of that, I added a template parameter that lets the user decide if the winding direction is already known in advance at compile time. If the winding direction is already known at compile time, we don't need to do any of that cross-product stuff, but simply just take the information that the caller supplied. In any case, we still need to check that the range contains enough points for there to be something to render in the first place. My algorithm does fine even if there are fewer than 3 points, but it does require there to be at least 1 point, so I will explicitly check for an empty range. Then we get to the rasterizing loop. We need several variables. The current iterator on both sides as we go clockwise on one edge and counterclockwise on the other edge in the ring of vertices. The current slope for both edges. The current y-coordinate, the y-coordinate where the next event is on both sides, and an integer that identifies which side the next event is going to be. When the loop begins, we are already at an event because both edges point at the top left vertex. And we have to walk to the next vertex. This handles the situation whenever the next event is reached. The main task to be done is to go to the next vertex. If we are on the side that goes forwards in the chain, we advance the iterator, and if we reach the end, we loop back to the beginning. If we are on the side that goes backwards in the chain, we decrement the iterator, except if we were already in the beginning. We choose the end pointer first before decrementing it. Just basic circular iterator operation, which we have seen so many times already in this series. Once that is done, we calculate the new slope for that side and identify where the next event is going to be. It is done by comparing the y-coordinates at the end of the current line on both sides. Then we process scan lines just like we did before. And this is the finished function. Apologies about the small font size. I wanted to fit the entire function on screen, but I didn't want to delete any of those comments. If you watch this in 720p or greater, the text should be perfectly readable. Generally I try to keep everything legible and for 80p, but sometimes you also need to provide the big picture. Then I turned my attention back to the drawPolygon function. Inspired by the idea where I gave a template parameter for the winding direction, I decided to address another issue that was raised in the comments of the previous videos, hard-coded indexes. So far my drawPolygon function has assumed that the x and y coordinates are the first 2 elements in the points and that the z coordinate is the third one and so on, but it doesn't need to be that way. I decided to rewrite this function in such a way that the function no longer makes any assumptions whatsoever on the layout of the points. Instead, all of that information is given as template parameters. I also added a template parameter that lets the caller choose whether the rendering should be perspective corrected or not. If they don't want perspective correction, then the z-index will be ignored, as it no longer has any special meaning and the points don't even need to have a z-coordinate. Unfortunately, this means that I will have to reintroduce that unsightly compile time for loop again, because now I am going to deal with those numeric indexes which I don't know in advance. The code will lose the prettiness that it had, but it will gain leaps in terms of genericity. I also now call the rasterize polygon function directly, completely skipping the tessellation step, increasing the performance of the renderer by some amount, I presume. Note that when I speak about performance in this series, I am not implying that my code is very efficient. This probably wouldn't run very well on 486. To gain the perfect performance, you need micro-optimizations, which I have not done in this series, and which I am not going to do because that's not the point. You will find some micro-optimizations in the code that is downloadable through the links I have provided, but the main purpose of this series is to teach and demonstrate you concepts in a way that you can intuitively understand, learn and even memorize, not to provide a high-performance 3D engine. In any case, once I finished making all the changes to the drawPolygon function, I evicted it into its separate template header file, just like I did with the other functions in this file so far. Next I focused on the main function. It contains some stuff that has no particularly good reason for being in the main function, such as the perspective projection and frustum stuff. I evicted that code into a new header file called view. I will convert this code into a class. The purpose of this class is to deal with everything concerning the viewport dimensions, including the frustum, the projection calculations, the pixel buffer, the Z buffer and depth checks. Since this is pretty mechanical work, let's run the music for a while. And there we go. Let me explain that last bit. This draw function, hold on, let me zoom on it. This is again a modern C++ thing, but if you have experience with functional programming languages like Scheme, this is already familiar to you. Shortly, this is a function that takes as a parameter another function and produces as its return value a different function that calls the supplied function. Let me peel it to you like an onion. Inside here we have a function. This function takes as a parameter some x, y, z coordinates and any number of other parameters. The function does a z buffer check. If the z coordinate was closer than what was already present at those coordinates, it saves the new z value in the buffer and calls the user supplied functor using those very same parameters that it itself received. The result of the user-supplied functor is a pixel, and it is saved in the pixel buffer of the view. This function is what the draw function returns. The draw function returns a function. The user supplies a function that calculates a pixel color given some parameters. View.draw converts this function into a new function that draws the pixel in its internal buffer. Then the user can supply the resulting function to drawPolygon. The outcome is that each component can concentrate on what they are really doing. The user-supplied plot functor does not need to care about the physical layout of the screen. The view does not need to care about the colors or textures or any of that stuff. The drawPolygon function does not need to care about either of those. Of course, there are other ways to accomplish the same, but in my opinion, this way all the different components require less knowledge about each other's. The main module just pulls strings to make things happen. It's like hiring different contractors to do different stuff without telling any of them what their work is going to be used for. The compiler will sort out what you are trying to accomplish and puts the pieces together and produces hopefully just as efficient code as if you had done it the traditional imperative way. Now let's review the new structure of my project. I have the main module, which is renderer.cc. First I moved the polygon clip and polygon draw functions into separate files. The polygon draw function depends on the slope class, which is also in a separate file. It also depended on the tessellation routine, which called the rasterizer, which was the first thing I wrote in this series. But then I changed the rasterizer to rasterize arbitrary polygons, which enables me to skip the tessellation step, making polygon draw call the rasterizer directly. All of these of course depend on the math module. And just now I added the view class, which is essentially the frame buffer and also contains the projection and frustum calculations. And of course the main module depends on libstl2, which acts as a glue between my program and the operating system. I like to have as few dependencies as possible, but concepts like screens or keyboards are not covered by the C++ standard, so I need some platform-specific stuff to deal with them. Rather than to create an implementation for some API in some operating system, or God forbid all of them, I use a well-known library that has very good support for all major operating systems, and then some. My main module still has plenty of roles, but this is an iterative process. Next I redesigned the renderer. I created the separate renderer function, which takes as its parameter a range of vertices, a range of polygons and other stuff. Actually I just copy-pasted the rendering stuff from main, but then I modified it. The supplied polygons are first transformed using the supplied transformation function, which does stuff like moving and rotating the world so that the player is at the center. Lastly, they are rendered using the drawPolygon function, which gets the user-supplied plot function modified by the viewsDraw method, as I explained a few minutes ago. I also enabled backface culling and told the drawPolygon function to expect that my polygons are always in clockwise orientation to save it some work. The other changes that I made are just stylistic changes that seek to reduce the number of magic constants in the file. Then going back to the main function, I rewrote the part that I just copy-pasted, turning it into a call to the render function. The render function is called with two functors, one which transforms the world, and the other is the functor that assigns each pixel a color. The color functor called plot works like this. It reads a texel from the texture at the supplied u and v coordinates, and it returns that texel. That's it. Next I will evict the level map creation from the main function and put it into a separate function. I also refactored it very slightly. Once again, this cuboid thing is just something I copy-pasted from the 75,000 subscribers demo, and it will be the first thing that will be gone in the next episode, but for now I still have to maintain it just for a little bit, to work with my new scheme for level data, where I split the data into an array of vertices with a separate array of polygons. Then I add a call to this createLevelMap function in the main function, and we are done. Because this episode was mostly about refactoring, there is not much new to demonstrate. But that will change very soon. In the next episode we will start exploring lighting effects, beginning from simple per vertex lighting like Descent did, and in the third episode we will go with full-blown global diffuse illumination with Radiosity. After that I still have much planned, so stay tuned. See you again. Bye.